This video introduces another example of a Marlowe financial contract, this time taken from the ACTUS Standard for financial contracts. And we'll start off by talking about that. What the ACTUS organisation have done is build a standard which gives a taxonomy of the different kinds of financial contracts that there are out there. Obviously, there are some highly exotic ones, but this is trying to give a classification and description of the commonest kinds of financial contract. So they produced a taxonomy and a substantial 60-70 page document that describes these in a high degree of detail. We've been talking to the ACTUS organisation, and what we are keen to do is see how those contracts, some of the representative sample of the contracts that ACTUS people have written, can be translated onto blockchain and put inside Marlowe. You can see here the link to the ACTUS web pages where you can see this taxonomy and you can read the description in a lot more detail. The example we've decided to look at is what's called a zero coupon bond. So it's a bond, it doesn't pay any interest, but when it matures, it delivers a profit. So just to get the terminology right, the bond is made or issued by an issuer and it's bought by an investor. At the start date of the bond, the issuer receives the notional value, the value on the bond, minus a discount. And then the issuer pays back the full value at maturity date. So they receive less than the full value at the start, but they pay back the full value on maturity, hence the profit for the investor. Okay, now how does this look in Marlowe? Well, before we do that, we should think about how we can ensure that the bond will finally be redeemed. We could say, well, the issuer must commit up front the money that they would need to pay back the investor in full at the end. But that makes the nonsense of this as an investment instrument. If they have the money, why would they need to borrow it? So there's no that's not a realistic model. We can simply say no guarantee is provided. The investor will take a risk, and that's, in a sense, that's how things are on in the real world. Investors do take a risk, and that's why they're gaining a profit, because they're taking a risk. But there is a third approach, and that is that a guarantor makes a commitment which is analogous to collateral. And we can think in a more complex model where we're able to model off-chain collateral on the chain. Then this is the way we've modeled it here allows us to take into account the fact that somebody can underwrite the repayment by the issuer. Even if the issuer can't make it, then the guarantor can. So let's see how this looks in practice. It's worth starting off just by looking at the top two lines. So what these do is they describe the type of the function that we've written, which you could think of as a template. And it says what parameters there are to the template, what are the things that need to be filled in to make an actual concrete contract. And if you look at the second line, we've given names to those various parameters. So we have we have three parties involved. We have the issuer, person issuing the bond, the investor, the person buying the bond, and the guarantor. We have two values for the contract. We have the notional value and the discount, which are both going to be positive integers. And we have two times, the start date and maturity date. And given all of those, what we get back is a contract. Now let's see what the contract actually does. If you look on the first what we do to start with, we have a when construct with a single case in it. What we're doing here is we're waiting, first of all, for the guarantor to deposit in the contract the notional amount. And when that happens, we wait for the investor to deposit in the contract the notional amount minus the discount. Now, if either of these fails to happen, we simply close the contract down. So at the in the case of the guarantor not doing anything, there's nothing to close down. In the case if the guarantor has put money into the contract, but the investor has not, what the close does is refund the guarantor's money from their account. So what happens? Let's suppose now that the deposit has been made by the guarantor, and then the deposit has been made by the investor. What we have next is an interesting construct. It's a when with no cases. So there is nothing here to succeed. And what is the purpose of this is to say we wait until the timeout happens. So what this says is wait until the start date and then do what comes next. And at the start date, we have a payment from the investor account to the issuer, the available money in that account, which we know is the notional minus the discount. So at that point, at the start date, the issuer gets their money. And then we wait. We wait for the issuer to deposit the notional amount, the full amount, into the investor account. And then when that has happened, we close. And here we wait until maturity date. So presumably the issuer will only put it in close to maturity date. But if we hit maturity date and the issuer hasn't made the payment, then we make a payment from the guarantor account to the investor account, the available money in the guarantor account, which we know is the full notional value. So that describes precisely how the contract behaves. And as you can see, it's in pure, precise terms, explains exactly what we explained earlier using English. But the nice thing about this is that there is no ambiguity about any of the terms. Once we understand the semantics of Marlowe, we have a clear description of how this contract behaves. Okay, so now we've seen a number of examples. What I want to do next is talk about a tiny bit of theory that underlies Marlowe, and then what we'll do is look at the Marlowe playground. So this is where we can put a lot of these ideas into practice.